Hello, my name is Gavin Cole, and this is my presentation for Python solutions to electrical engineering related problems. This is for Dr. Chapman's EGR214 engineering numerical methods. To start, it is important to know what numerical methods are and why they are important. Numerical methods are mathematical tools used to solve numerical problems. This is typically done using computer programming, and in our case, using the Python programming language. Numerical methods are important, especially to engineers, because they are efficient, accurate, and repeatable, making computations far easier and better overall. Here's problem 1. Faraday's law characterizes the voltage drop across an inductor as V sub L equals L times di dt, where V sub L is voltage drop, L is inductance, and T is time. Determine the voltage drop as a function of time from the following data for an inductance of 4 henries. And here's our table of time and current. We can describe the relationship between voltage drop and time by making a line plot, but before doing so, we will calculate the derivative using rise over run and multiply that by the inductance of 4 henries. Matching these values with the corresponding t values yields this graph. Now here's our Python program that solves the same problem. Notice up top that we have our t and I values already in a list, along with an empty list, t underscore voltage. We will append that with the voltage drop values that we will find later. We then set up and plot our voltage drop, same as before, towards the bottom. And here's the graph that was made along with the values of the voltage drop. Moving on to problem 2. Using Kirchhoff's rules, the impedance of an LRC electrical circuit can be described by this equation, where Z is impedance and omega is the angular frequency. Find omega that results in an impedance of 100 ohms using the Brent Q function with initial guesses of 1 and 1000 for the following parameter values. R is 225 ohms, C is 0.6 times 10 to the negative 6 farads, and L is 0.5 henries. Here's the analytic solution. Notice that towards the end we make a substitution, and we are then able to put this into quadratic form and solve for the roots. The quadratic formula yields omega to have the solutions 204 and 1.51 times 10 to the 4th. Now here's our Python solution. Notice we have already solved the function for z by taking the reciprocal of the entire function. Also notice in the second and third argument of the Brent Q function towards the bottom that our guesses are 1 and 1000. This means we will get the solution for the equation that is between these two initial guesses. Now notice that when we solved analytically for the answer, we got 204 for omega, which is a little off. However, if we plug it back into the function, we get a number that is very close to 0, meaning that our first answer was off quite a bit. That is probably because of how we rounded our answers. In conclusion, numerical methods assisted us in 2 different ways across these 2 problems. In problem 1, it made the calculation far quicker, and in problem 2, it made a far more accurate calculation. However, the most important feature that numerical methods has is that it is repeatable. The code can be replaced in part to solve a similar problem, which is very efficient. This shows the usefulness of numerical methods in larger and more complex environments. Thank you.